See, now we'll try to find the position of center of mass of a hemisphere. Think how to find the position of center of mass of a hemisphere. See, question is given a hemisphere, you have to find the position of center of mass of this hemisphere. Say let R be the radius of the hemisphere. How we are going to solve this? How to find the position of the center of mass of the hemisphere? Think. And let M be the mass of this hemisphere. See, to find the position of the center of mass, if it is hemisphere, hemisphere will be divided into many small elements of disks. So what I will do, I'll consider a small elementary disk of thickness dx and radius of the disk is y, and this elementary disk is at a distance of x from O. So I should find the position of the center of mass. Let it be C. How to find the position of the center of mass? See, you know, xcm is the position of the center of mass along x-axis is 1 by m into integration of x dm from 0 to r, lower limit and upper limit. It means first I should know how to find the mass of the small elementary disk. How to find the mass? You know this, just you think how we are going to find the mass of this small portion. dm is the mass of the small elementary disk, and the dm is equals to density into volume. You know that density is equals to mass by volume. Density into volume of this small elementary disk. And how to find the volume? Think again, volume, area into this thickness. Area into dx. So dm is equals to rho into, what's the area of the disk? Pi, here r square, but radius is y. Pi into y square into dx. dm is equals to rho pi into, what is y? Y in terms of r and x. See here r square is equals to y square plus x square. Y square is equal to r square minus x square. So dm is equal to rho pi into r square minus x square into dx. Substitute this value in xcm equation. 1 by m into integration of x dm is rho pi into r square minus x square into dx from 0 to r. If you know the integration, then this sum is very simple. How to find the integration? 1 by m into, look at this equation, rho pi constant terms. So I can write that constant terms outside the integration. Rho pi by m into integration of x r square dx. Means integration of x dx is x square by 2 into r square minus integration of x cube dx, which is nothing but x to the power 4 by 4 from lower limit to upper limit. Use the integration of x to the power n dx formula, x to the power n plus 1 by n plus 1. Substitute the values. Rho pi by m into, what is upper limit here? R. X square r square by 2. If we substitute the value of upper limit, so it will be r to the power 4 by 2 minus r to the power 4 by 4. Rho pi r to the power 4 by, this is a mass of the entire hemisphere, into half minus 4. Take LCM. You know how to find the value. 4 is the LCM. So 2 minus 1, which is 1. Now, till here it's easy. Rho pi r to the power 4 by 4m. Find the value of mass of hemisphere in terms of density. Again, same thing. Mass is equals to density into volume. What is the volume of the hemisphere? Therefore, mass is density into volume of hemisphere. Density into, what's the volume of hemisphere? I told you it's 2 by 3 pi r cube. Substitute the value. So which is xcm is equal to rho pi r to the power 4 by mass of the hemisphere, rho 2 by 3 pi r cube into 1 by 4. So you can cancel rho pi and here rho and pi, r to the power 4 and r. So xcm is equal to 3 by 8 r. So xcm value is 3 by 8 times the radius. So position of the center of mass of the hemisphere along x-axis is 3 r by 8. Along y-axis it is 0 and along z-axis is also 0. What are the coordinates then? xcm, ycm, zcm is equal to 3r by 8, 0, 0. See, if they give any object, if you know the volume of that particular object, it's easy for you to calculate the position of center of mass. Remember, first you have to consider a small element, find the mass of that small element, and then substitute the value in the formula. xcm is equals to 1 by total mass of the object into integration of x into dm. Integration from lower limit to upper limit. You will get the position of the center of mass of a given object.